So welcome you back. So last couple of lectures we discussed about elements of statistical inference problem. So where essentially I described what are the statistical inference problems. They can be broadly categorized into two categories. One is called the non-parametric statistical inference, and then the parametric statistical inference. And then I said that for the purpose of this course, mostly we'll be restricting to non-parametric statistical inference. And then we talked about the elements of any statistical inference problems. So every inference problem has three elements, which is P, the class of all family of probability distributions under consideration. Then there is an action space, which tells you, based on the random experiment which you perform, you observe a random variable and what action to take after you have observed a random variable x. And then every action has certain loss associated with it. So we talked about the loss associated with any action A. So these are the elements of any statistical inference problems. Then we talked about the decision rules, or in the case of estimation, they are called estimators. So to study the decision rules in the generality, we introduced the concept of randomized decision rules. And we said that randomized decision rules sometimes are necessary where you need two stages of randomization. So after you have performed the experiment, you don't immediately take the decision. You do another stage of randomization before you go for a final decision. And then the usual decision rules, which we call as non-randomized decision rules, are basically particular case of decision rules where the corresponding probability distribution is degenerate at a point. So that means immediately after observing the random variable x, you take the decision. Then we realize that the problem with statistical inference problems is that if I consider a general decision problem and consider the class of all general decision rules, it's not possible to find the best decision rule. And that is due to the fact that the class of family of distributions is unknown. So it may be a large class. So it may not be possible to find a decision rule which minimizes the risk function for every element in P. So then we say that what we do is we put reasonable restrictions on the class of decision rules under consideration. And then by restricting our class of decision rules under consideration, we try to find out the best decision rule in the restricted class, and that is possible in many situations. So when you did last course, one that reasonable consideration was the unbiasedness in case of estimation problem. So you said that your estimator should be unbiased. That means in the long run, on an average, it should give me the correct value of the parameter which I want to estimate. And then we realize that once you impose this reasonable restriction, the class of estimators under consideration has become small, and then it is possible to find the best estimator. So similar criteria is invariance. So in certain situations, you would realize that your estimation problem under consideration has a structure which is invariant under certain group of transformations. Now, if that is the case, then the principle of invariance suggests that I should only consider decision rules which are invariant. So here further, the class of decision rule under consideration has been restricted. And in many situations, it so turns out that the risk of any invariant estimator turns out to be a constant function. So I'm no longer talking about minimization of a function for every parametric point theta, because all these functions are constant functions. So it may be possible to find a decision rule for which this function, this constant function, is the minimum. So this is all we did, and then we talked about the location invariant estimation. So what I'm going to do today is I'll talk about some of the applications of the results which we did in the last couple of lectures. So to see the first example, let us look at the following. So what you have is x1, x2, xn is a random sample from a normal distribution with mean theta and variance 1. My theta is unknown, which belongs to capital theta, which in this case I assume to be whole real line R. Goal is estimation of theta under the squared error loss function. So my loss function is squared error. Now we talked about the fact that convex loss functions are reasonable choices of loss functions, because the value of this is 0 when my xn is same as the true value, and my loss increases as my xn is far away from the actual value theta. So this is square error loss function. Now, square error loss function is always convex in A for every theta. Convex in A for every theta. Now this is straightforward to verify. You can just take the derivative with respect to A for every fixed theta. Double derivative is 2, which is positive, so it is convex in A for every theta belonging to theta. Now you know that if your loss function is convex, then your life has already become very simple. First of all, I need not bother about all the randomized decision rules. I can only talk about non-randomized decision rules, which are easy to evaluate. So let's try to see applications of those results. Why for convex loss function? Because we did a general result. We said that, look, if your loss function is convex, then given any randomized estimator, you can find a non-randomized estimator whose risk is smaller than the given randomized estimator. So that is the one result which we did. We also did a result in general which says that if you are given any decision rule, then you can find a decision rule based on minimum sufficient statistic whose risk is same as the given decision rule. So to see applications of that, so let us see, consider the non-randomized. This is a randomized decision rule. So consider the randomized decision rule delta naught minus infinity to t given x as phi of t minus x1. So let us try to revisit what was the definition of a decision rule. A decision rule is a probability measure. So this delta naught is a probability measure. And it says my non-randomized decision rule is a probability measure whose distribution function is that of a normal with mean x1. So that means here the corresponding random variable over here is normal with mean x1 and 1. So what this randomized decision rule does is, after observing x, it looks at the first observation x1. Once you have observed x1, x2, xn, it doesn't bother about x2 to xn. It only looks at the first observation x1. And then it generates one observation from a normal distribution with mean x1 and variance 1. And whatever that observation is, that is taken as a estimator of theta. So there are randomization in two stages. First stage is I observe x1, x2, xn. Then I just only look at x1 and generate another observation, which is a second stage randomization from a normal distribution with mean x1 and 1. And whatever is the output, I take that as an estimator. So this is a given randomized decision rule. So let me do the following two problems. Find randomized estimator say delta 1, that is a function of minimal sufficient statistic and has the same risk as delta 1. Second part of the question is find a non-randomized estimator that dominates delta naught and delta 2x, which is same as x1. So let us try to do these problems one by one. So the first part says that this is a randomized estimator which does not depend on the complete sufficient statistic. The complete sufficient statistic in the normal theta 1 case is x bar. So that is the first thing I should write it down. X bar is complete sufficient and hence minimal sufficient. All right. Now this randomized decision rule only takes the first observation into consideration. Now we have done a result that if you are given any decision rule, whether randomized or non-randomized, which is not based on a minimal sufficient statistic, you can find the one which is based on a minimal sufficient statistic and has the same risk as the one which is given to you. So that means I can find an estimator or a decision rule which is based on x bar and has the same risk as that delta naught. And if you see that result, we had constructed such an estimator. And what is such an estimator? Such an estimator is nothing but expected value of this probability measure when x bar is given to us. So that is delta 1 x is nothing but, so this would be, so let us look at delta 1 would be a probability measure. So these are delta 1 minus infinity to t given x is nothing but expected value of that, expected value of delta naught minus infinity t given x bar is equal to x bar, right? That is what my estimator is. So conditional expectation of the given probability measure given that x bar is equal to x bar. But what is this? This is phi of t minus x1. So this is same as expected value of, what is the delta naught minus t given x? Phi of t minus x1 given x bar. Sorry, phi of t minus x1 given that x bar is equal to x bar. This is what it turns out to be. I've just put the value of delta naught minus infinity to t given x. Now, here I am talking about conditional distribution of x1 given x bar. Of course, we know the conditional distribution of x1 given x bar. That's not an issue. I can make it slightly simpler. So what I do is I write down this as expected value of phi of t. Because x bar is given to be small x bar, so I subtract x bar and then minus x1 minus x bar. Because this x bar is small x bar, so they will get cancelled. Given that x bar is equal to x bar. Let us try to see what is the distribution of x1 minus x bar. x1 minus x bar is linear combination of independent xi's, because x bar is 1 upon n summation xi, and then x1 minus that would be same as summation ci xi for some ci's. So it is linear combination of independent normal variables. And you know that linear combination of independent normal variables is again normal, with mean as the mean of x1 minus x bar. Mean of x1 minus x bar is 0 because mean of x1 is theta, mean of x bar is also theta, so 0. Variance of x1 minus x bar, so that is same as variance of x1, 1, plus variance of x bar, 1 by n, minus 2 times covariance between x1 and x bar. Now note that x bar has x2 to xn also. So the only covariance factor which will come only through x1 upon n. So it will become covariance of x1 and x1 by n, which is 1 upon n variance of xn, so it becomes minus 2 by n. So this is normal 0, 1 minus 1 by n, so n minus 1 by n. So what do you get over here? Distribution of x1 minus x bar does not depend on theta, so it is ancillary. X1 minus x bar is ancillary, x bar is complete sufficient. So by Basu's theorem, x1 minus x bar and x bar are independent. And if you see over here, the small x bar is a fixed quantity. So this expectation is to conditional distribution of x1 minus x bar given x bar. Since the two are independent, so this expectation would be same as unconditional expectation. So this is same as expected value of phi of t minus x bar minus, let me call this as z. Conditional is same as unconditional, where z is x1 minus x bar, which is normal 0, n minus 1 by n. Now note that this can always be written as minus infinity to infinity phi of t minus x bar minus z 1 by the density of z, so 1 by sigma root 2 pi e to power minus z square by 2 dz, 2 sigma square. So this is my sigma square. Now note that this whole integral can be written as probability that z1 is less than or equal to t minus x bar minus z2, where z1 is normal 0, 1, z2 is nothing but normal 0 sigma square, right? Why? And z1 and z2 are independent. That is very clear because this probability would be same as I fix z2. z2 can go from minus infinity to infinity. Probability that z1 less than or equal to t minus x bar minus z2, given z2 is equal to z, then multiplied by theorem, multiplied by probability density of z2, which is this, by theorem of total probability. So probability of A given B, and then the probability density of B, and then this z has been allowed to vary from minus infinity to infinity. Now here, z2 I can put as small z, there is no problem. Once I have done that, then z1 and z2 are independent. So this probability would be same as probability z1 less than or equal to t minus x bar minus small z, which is equal to phi of t minus x bar minus z. So the two are same. So this probability can be written as this. Let me just not remove the second part. So what do you get over here? So this is same as probability that z1 plus z2 is less than or equal to t minus x bar. What is the distribution of z1 plus z2? It is a sum of two independent normals, so it is again normal What is the mean? Mean of Z1 plus mean of Z2. Mean of Z1 is 0. Mean of Z2 is 0. So the mean is 0. Variance of Z1 plus variance of Z2. Variance of Z1 is 1 plus sigma square. So this can be written as phi of Z1 plus Z2 minus B, so T minus X bar by root of 1 plus sigma square. So this is what it is. So this estimator, delta 1 minus infinity to T given X turns out to be phi of T minus X bar upon square root of 1 plus sigma square. Of course, sigma square, you know, is nothing but n minus 1 by n, which is known to us. So I had a decision rule delta naught which depended only on x1, and what it was saying is you observe x1, x2, xn, ignore x2 to xn, consider only the first observation x1. Now generate one observation from normal with mean x1 and variance 1, and whatever is the output you take that as an estimate. Then from the theory which I did, I knew that there will always exist a randomized estimator depending on the minimal sufficient statistic x bar, which would have the same risk function as the given estimator which is only depending on x1. And we have obtained from the construction used in the theory that such an estimator would be this. So let us try to interpret this. What does this say? This is exactly the same as that, except that now it says that it depends on x bar. So what does estimator says? So it is a probability measure of normal with mean x bar and variance as 1 plus sigma square. So it says you observe x bar, you observe the sample, calculate the x bar. Now generate one observation from normal distribution with mean as x bar and variance as 1 plus sigma square. Whatever is the output, you take that as an estimator. So this is the required estimator. So now let us consider the second part. Now I have to find a non-randomized estimator that dominates delta naught as well as this quantity. And it is possible to get a dominating non-randomized estimator because your loss function is convex. So if you recall the theory, our theory said that, look, if your loss function is convex in A for every theta, then first stage randomization is not necessary. Whatever randomization is there in the first stage, whatever random variable is there, take its mean so that randomization is gone, and that would be the non-randomized estimator, which would be dominating the given randomized estimator. So if I have to find an estimator dominating delta naught, so delta naught T minus X is nothing but phi of T minus X1. So that means my Y of X is nothing but normal with mean X1 and variance 1. So if I have to find an estimator dominating this, what I have to do? It says you just consider expected value of Yx. So let me call this as delta naught star x, which is expected value of, and is not necessary. So it says delta naught x. Just take as expected value of y of x. Delta naught star, you can put it. But the random variable over here is normal x11, so its mean is x1. So because my loss function is convex in A, so this dominates delta naught. Now let's look at the estimator which dominates delta naught delta 2. So this is now a randomized estimator itself. So I have to find an estimator which dominates. So first I obtained the estimator which dominates the randomized estimator. which is x1, which is a non-randomized estimator. He says now you find an estimator which dominates this. Now, we knew that such a thing is possible if your loss function is convex using Jensen's inequality. And what will be the estimator? You take expected value of x1 given x bar. So, the is dominated by delta 2 star x x1 given x bar is equal to x bar. Sorry, delta 1 given small x. That is what it says. Condition on complete sufficient statistic and take the expected value of given estimator. Of course, we knew that it does not depend on theta, it is a proper estimator. Why? Because x bar is sufficient. So, conditional distribution of x1 given x bar will not depend on theta. So, it is a proper estimator. So, you need to consider conditional distribution of x1 given x bar. Of course, one can find out what is a joint distribution of what is a conditional distribution of x1 given x bar. One way to do that would be x1 and x bar will have a bivariate normal, right? Why? Because you know that a random variable has a bivariate normal if and only if all linear combinations have a univariate normal. So, all linear combination of x1 and x bar are some linear combination of x1, x2, xn, which are independent, so that will have a normal distribution. So, that means all linear combination of x1 and x bar are univariate normal. So, x1 and x bar have a univariate normal, sorry, bivariate normal. So, in fact, you can do it this way. I'll show it the other way also. What is the mean of x1? Theta. What is the mean of x bar? Theta. What is the variance of x1? 1. What is the covariance between x1 and x bar? 1 by n. What is the variance of x bar? Sigma square by n, which is 1 by n. So, now I know that x1 given x bar is equal to x bar, because in the bivariate normal case you know that conditional distributions are univariate normal. It is normal with this plus covariance then inverse of this, and then sorry, I made a mistake. If you recall, it would be normal x bar, the mean of this thing, plus covariance is 1 upon n, then the variance, and then x bar minus the mean of over here, so that is theta. And what is the variance? Variance is variance of this minus covariance inverse of this into 1 by n. So, which is normal x bar and 1 minus 1 by n. So, delta 2 star x, that way turns out to be expected value of x1 given x bar is equal to x bar, which is same as x bar. You could have gotten this using Basu's theorem also. Delta 2 star x can always be written as expected value of x1 given x bar is equal to x bar, which is same as expected value of x1 minus x bar plus small x bar given x bar is equal to x bar. Now, here this x bar is fixed, so that goes outside the expectation. Just by the argument I used few movements back. This is ancillary. This is complete sufficient. So by Basu's theorem, the two are independent. So conditional expectation is same as unconditional one. So this is same as expected value of x1 minus x bar plus x bar. Expected value of x1 minus x bar is 0. So this is same as x bar. So this is one example where we saw applications of the theory which we did.